recording.
Hi everyone. So welcome to our podcast. This is our 10th episode and today we are talking with Akash. I'm really happy that Akash is here and he has published a really nice paper and he'll be talking about it mostly. By trade, Akash is right now a data engineer at Shell, but he is very much interested to share his research and he was really interested in the podcast because it's giving a space for young researchers for him to show what they have researched on their papers and all. So without further ado, let Akash take over. And Akash, please introduce yourself. Talk a little bit how you are working at Shell. What's your day-to-day responsibility, and then we'll move into your research and talk about it really in detail.
Thank you, Tanishta and Isha. So thank you for inviting me for this podcast. Yeah, thank you. And this is a good platform for young researchers and all the industry people also. So yeah, so let me give my introduction. So thank you, everyone. So my name is Akash Debnath. I did my master's from ITSM Dhanbad in applied geophysics. Then I joined NJRI, National Geophysical Research Institute, as a project associate. So there I worked for 9 months, and I published at least three papers there with my guide also. And then I joined Shell as a process data engineer. So in 2021, I joined Shell, and now I working at Shell around 1.5 years now. So yeah, that's all about for me.
Maybe
Yeah.
I can start sharing your presentation. And okay, so
Can
just
I?
a second.
Okay. Yeah.
Full screen would be better. Okay,
Okay.
okay. So Akash, tell us about ToC prediction with Bayesian multivariate model. So maybe I'll just ask you a few simple questions. What is ToC? Total car, like, yeah, maybe you can explain
Yes.
a little bit better. Yeah.
Yeah. So ToC is nothing but a total organic carbon. So it's a very important thing if you want to explore in exploration to explore oil. So ToC is also a good attribute to predict to explore the oil in any reservoir. So it's always we are till now a lot of researcher have been done to predict that ToC. If you don't have the log data, you
Mm-hmm.
cannot detect the ToC directly. But using different logs, we can predict the ToC. So and number of technique we can do, and what we have tried to predict the ToC using Bayesian multivariate model, and
Mm-hmm.
so it's a approach on the prospect of geostatistics based prediction. So it's
Mm-hmm.
totally geostatistical way we can predict the ToC. But
Mm-hmm.
so nowadays lot of also research happening using machine learning. So but for machine learning also you need a lot of data sets. So also so geostatistics also a good things that we can have the idea about the uncertainty also.
Mm-hmm.
So it's a good thing in the geostatistic part, and
Mm-hmm.
it's a totally data driven approach to predict any parameter. So
Right.
that's
Okay.
so can I
Okay.
start or any question if you have?
I was trying to do a slideshow. Okay. Yes. Okay. So this is a, yeah. Please start.
Okay. Okay. So yeah. So this paper is was published last year. So me and my guide Shiv Shankar Ganguly was and also uh, um, two people we are combinedly work on that and publish this paper, and it was a good work. We and this work is totally done on Python coding.
Mm-hmm.
So we work a lot. The data sets in the world is really good, and it's I got the good result also. So for that, so yeah. So let me start.
Sure.
So today let's know about the what is geostatistics. So geostatistics if you see that offers a means to quantify the uncertainty. So
Hmm.
uncertainty is a always a good if we know the uncertainty, it always to be have a good to predict anything, that what is the range, up to range, what are the uncertainty we can get in any parameter to predict. So let's start from statistics. So statistics is nothing but a collection of the data, and we have to organize the data sets, and using and depending on the data sets, we make decision on that, and
Hmm.
also draw some conclusion that what are the things we need to what are the decision we need to make depending on the data sets. But the geostatistic is a it's also a part of statistics, but it has a special context, and also special relationship also, and volumetrics are both, and also it has an uncertainty also. Yeah, next.
Okay.
So why we are using geostatistical model? Why not deterministic? So let's know about the deterministic model. So deterministic
So
model is
what is
nothing.
the sorry to bother you. What is the,
Yes.
can you explain a deterministic model first, maybe?
Yeah. So deterministic model is nothing but if you know the relationship, if it's
Uh-huh.
one equation, that you'll get only unique solution for any
Hmm.
uh, equation. If you get unique solution, it's a deterministic model. So you
Okay.
will have only one model, and you will get only one unique result.
Mm-hmm.
Okay. So
Okay.
it's a deterministic model.
Yeah.
So it's completely predictable. Okay. But
Mm-hmm.
geostatistical model, you can get lots of model you can create. Okay, there is no one unique model will be not there, but
Mm-hmm.
taking the mean of this distribution, because it's a distribution, so in the distribution there is a lot of range of data sets, so we can say you the uncertainty, and also taking the mean of this distribution, we can get one model, but there is a lot of model can be
Mm.
present because
Yeah.
it's a distribution. Okay, so that is the difference between deterministic model and geostatistical model.
Mm-hmm.
And what is the advantage of the geostatistical model? That is, you can assess the uncertainty, and
Yeah.
also we have the data. It's also,
Confident. Yeah. Mm-hmm.
yes,
Yeah. Yeah.
confidence interval you can present, you can show, and also
Mm.
data driven approach is total data driven approach.
Right.
So that are the advantages we can have if you using the geostatistical model. Yeah.
Good. Good. Yeah. So yeah, we have learned a lot in geophysics, right, of
Yes.
Bayesian theorem, and I also
Yes.
remember that maybe, yeah, if you can, in a high level, let the audience know what
Yeah,
is the,
I have
yeah,
also attached one example also to
yeah,
understand better. So as we read that Bayesian theorem, that this the equation.
yeah,
So if you know the prior likelihood, so we can get the posterior. So it's
mm-hmm,
nothing but some information of an event,
mm-hmm,
and you depending on that information, you will predict another event, what the information you have. Okay,
yeah,
so this is the thing, like if you know the prior information, if you have, we can predict the posterior. So, okay,
mm,
so using this method, Bayesian theorem, will predict the ToC. So we'll create one equation. We'll use our prior information, and using those information, we'll predict the ToC. What is my posterior?
okay,
So this is a simple equation we have. So next I have attached one example,
mm-hmm,
very simple
yeah,
example. I think it will help to understand how Bayesian
mm-hmm,
works. So if you see that one example, so prior information at a site suggests that channel feature exists at a given location with probability 60%. Okay, so and we decide to further investigate this information using seismic data.
mm.
So seismic survey can show a feature is present with 90% probability.
What kind of feature? Like this is from the
It
seismic
can be fault,
images?
anything. Yes,
Okay,
yes,
I see. Mm-hmm,
anything features. So if
okay,
if its presence is 90% probability, and if it's really is present. Okay, if you know it's
yeah,
present, but your probability to predict that it's present or not is 90% you get. Okay.
Mhm. Mhm.
And the probability it's not present, it's the 70%.
Mhm.
If it's really is not, if not, you know that it's not present, but your Bayesian theorem will give the 70% confidence that it not present. Okay. So here the probability of a event, that is zero point 0.6, that is 60% of what I give in the example. If you see, so it
Yeah.
is zero point 0.6. Okay.
Right.
And
Right.
the probability of b, if you know the probability of a, that is zero point 0.9. So
Mhm.
here is the, you know the probability is 90%, but the event a is, you know that is it's present. So that's why the probability of b, if you know the a, it's zero point 0.9. Okay. And the probability of b complement, if you know the a complement, that is 70%. So that is zero point 0.7 in the fraction. So we know this all this pa and pb and b complements. So if we use the that Bayes theorem, so we can get the information that probability of a event, if you know the b, that is the feature is present, the probability of the feature, what is the probability of feature, it's present. If you know the seismic shows the feature, if you know the
Okay.
information of b event.
Yeah.
So if we use this all those value here, and we can get that is the value what I get at 82%. Okay. So using this way, we same way we try to use this Bayes theorem in our work also.
Okay. Okay. So
So
next.
just,
Mhm.
yeah. So now I want to just briefly want to explain one that is Markov chain Monte Carlo. So it's nothing but a sampling. So how you sample the data sets, because we are trying to create a model. It's totally
Mhm.
depending on the sample. But in the
Mhm.
sampling part, we are using Markov chain Monte Carlo. Okay.
Mhm.
So because there are a number of model will be generated for different sampling, but
Mhm.
we'll consider only those model which will give your minimum uncertainty. Okay. So here the Markov chain Monte Carlo, what it does, like uh, we can obtain a desired distribution, but the
Mhm.
distribution equilibrium. Okay, that is the main
Sorry,
thing.
the decide is what? Can you please repeat?
Where doing the sampling using Markov chain Monte Carlo, the
Yeah. Yeah.
probability distribution will be equilibrium. There will
Okay.
be,
I see.
yeah, like here I gave one example, like
Mhm.
if you see that there is one square and within
Yeah.
this there is one uh, uh, there is a circle. Okay. So if you
Mhm.
throw randomly some points. Okay.
Yeah. Over
So
here.
we can,
Oh,
yeah,
in the
so
square, right? Yeah. Mhm.
yes, yes. You're throwing randomly all these points over this image. Okay. And if you calculate that
Yeah.
what is the what is the value of pi. Okay. So what is the equation, like it would be 4 into circle area by the square area.
Hmm.
Okay. Now, if you throw either throw the points randomly, like 10,000 point or 1 lakh point you throw. Okay. After that, if you want to, if you calculate all those points within the circle and all over this square, and if you put this value in this equation, like 4 into uh, pi r square by 2 pi r, so that
Hmm.
you will get the pi value, right? But
Hmm.
same way, what we did that it would be 4 into points within the circle by point within the square. So if you give
Hmm.
the all this point, if you calculate the point, how many points within the circle and within the square, you will get the same value as pi, near about to pi. If you increase the
Hmm.
number of samples, you will get the value of pi near as much as near to pi. So this way it's the working principle, the Markov chain here. This is the main
Okay.
thing. So here the distribution is equilibrium. So that is the main one thing. It follows the Markov chain Monte Carlo.
Hmm.
So that is the one example I gave here. I think it will be helpful to understand
We
how
can
it's working.
ne go to next slide.
Yeah, yeah,
Okay.
sure.
So
So
that's the study area, right? Yeah.
yes,
Okay.
yes. So
Algeria.
that's
Okay. Mm-hmm.
yeah. So that is the area we one case we studied. Actually, we studied I think two cases, but I present here only one history and event. So the data sets I got we got the from this Algeria, Hanef Basin, southern Algerian Sahara. So thanks to my guide that he managed all those data sets from and we worked on this. And our target zone was Silurian shale. And what
Hmm.
are the logs data we got? That is gamma ray, density log, composited neuron, compressional sonic, uh, uranium, and thorium. Okay.
Thorium.
And
Okay.
yeah, and our
One question
objectives,
over here, Akash.
yes.
How big was your data set?
Uh, I think
How
I'm
many
not
wells or
sure.
maybe how many grammar data did you
Yeah,
have? How
I
much data?
we worked on two wells.
Okay, I see.
Two wells we
And
have studied.
okay, and how depth? How long was this well? Like the depth?
Uh, Depth was I think around 2,000 meters. I think.
Two 2,000 meters. Okay. Mm-hmm. Okay. No, I'm just trying to also think in terms of machine learning, right? Also because, but
Yeah.
also because this is also a
Yes.
data-driven
Yes.
approach, right?
Yeah. It's a
So if we
data.
had more data, then how it could have
Hmm.
been proved. Okay.
Yes. Yeah.
Yeah, please go on here.
Okay. Next.
Yeah.
So first of all, before doing any uh, using any, if you want to use machine learning or use anything, so first thing is we need to see the relationship with the logs and
Hmm.
what you will want to predict. So we have also the ToC value also. So why we try to represent the relationship here. So if you see properly that there is a linear relationship with the all other logs. Okay.
Hmm.
So it shows that there is a some relationship is there with the log
Yeah.
datasets. So we
Uh-huh.
can create one model,
Yeah.
okay, that will give our TOC value. So this correlation will give the confidence that we can create a one model. So this is the first thing we need to check. What are the
Hmm.
relation we have? Is it linear or non-linear?
Hmm.
So yeah,
Okay.
that is the thing.
Okay.
Next.
Okay. Mm-hmm.
So yeah, so here what after getting confidence from this correlation that there is a good
Mm-hmm.
relationship with the basic with the, all these log datasets. So we try to create one equation that is a multivariate equation. So here, if you see the TOC value is equals to one. I took one constant plus x1, x2, x3, x4, x5. These are our log value,
Hmm.
and beta 1, beta 2. These are the coefficients of this
Yeah.
equation. Okay. So we try to create this equation, and and the main thing here is the coefficient. If we know the coefficient value, we can predict the TOC value. Okay. Actually, because we know the x1 is log value we have. Okay.
Hmm.
So only thing is our coefficient. If we know the coefficient value, we can easily calculate the TOC value at any depth.
Hmm.
Okay. So we tried. So here, what we do, we did that. We use Bayes theorem. So we create that Bayesian multivariate equation, and
Mm-hmm.
the sampling we did that Markovchan Monte Carlo. Using that
Hmm.
Markovchan Monte Carlo, we did the sampling, and based on this sampling, using Bayesian theorem, we
Hmm.
uh, we got the posterior, that is the
Hmm.
TOC value, and
Okay.
this posterior would be like
Yeah.
there is also a what I can say like minimum uncertainty should be there. There is a
Huh.
but the if there will be lot of model we can generate. Okay, lot of posterior will be generated, but only that value would be considered if it come under this error, minimum
Yeah.
error. Okay, so here we assume that the distribution of those coefficient that is Gaussian, and mean is 0, and the standard deviation is 10, and the constant value that is beta 0, it's half Cauchy distribution. Okay, so these are
Hmm.
the assumption uh, we take. And after that, we use that Bayesian multivariate equation, and we did the sampling using Markov chain Monte Carlo, and it will generate a number of posterior. And the next slide we can this in the next slide. You know,
Okay. Yeah.
I can show you there. So here, if you see that this is the all those distribution, posterior distribution
Mm-hmm.
of the
Yeah.
coefficients we get.
Uh-huh.
So
Yeah.
using this sampling, so it doing 2000 sampling, and total two chain we used. So 2000 total 4000 sampling happened. And so here if you see that we get this distribution, there is a two chain if you see. And these are all are my posterior distribution after using Bayesian theorem,
Mm-hmm.
and using the sampling of using Monte Carlo Monte Carlo Markov chain Monte Carlo.
Mm-hmm.
So these are the posterior we got. Yeah. And
Okay.
okay, and if you see the value ToC equation, so here
Mm-hmm.
if you what the
Yeah.
if you see that value, so these are the mean, nothing but a mean of this distribution.
Mm-hmm.
Okay, so we get individual distribution for each coefficient of those multivariate equation, and
Mm-hmm.
we take the mean value of those distribution, and we create one simple linear equation that is if you know what it's written here. Okay, so
Mm.
this equation will give us the minimum error with the real data
Yeah.
sets. Okay.
Okay.
So also we try to present like we also
Uh-huh.
try to predict and the observed data here. If you see
Yeah.
in
Mm-hmm.
the left side,
Yeah.
so it's almost matching the predicted counts and the observed counts. It's almost matching, right? And also, if you see in the right part,
Mm-hmm.
here the red dots are the your reference, that is original
Yeah.
value, that is what I got in the data we got for ToC. And these are the models. If you see number of chains, number of line is drawing within
Yeah.
this. If you see, so these are the model we created. So
Mm.
geostatic
All
is,
these.
if
Yeah.
you know, yeah,
Okay.
a
Mm-hmm.
lot of model have been generated using the prior value, and it gives this posterior.
Mm.
So, but we need to consider only those that have minimum uncertainty. So we took the mean value of those distribution, and we got and we try to connect all those points. If you see the a little bit below on the right side, so
Mm-hmm.
these are the mean values that is in the blue color,
Yeah.
and and red dots are the original ToC value. So it's
Uh-huh.
almost matching. Okay, and also if you can see the 50% confidence interval and also the 95% confidence interval. So you know the ranges that, yeah, within this depth we can have the ToC value within these ranges. So this is a very important information for any exploration or reservoir geophysicist or something. So, so this one thing that geostatistics
Mm-hmm.
gave. So, and also we
Yeah.
can calculate the probability also, right?
Right.
So
Mm-hmm.
if you
Mm-hmm.
see, there is a probability, the maximum is 0.16, because if you think that the probability is very low, but there is this information also very important, because it will give you the some confidence that what will be the much more errorless ToC value would be. Okay,
Mm-hmm.
so so this is also a good result we got after using those uh,
Mm-hmm.
statistical approach. Yeah.
Okay.
Yes.
Yeah. So this is
Yeah.
low probability. Yeah. In the
Yeah. In the
middle.
middle
Mm-hmm.
part, if you see, the high probability is there.
Mm-hmm. Yeah. Okay. 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 So results. Yeah.
Yeah, these are the results we got. So
Uh-huh.
we try to compare with the some two other model,
Mm-hmm.
like it's already published, I think, that is GR based model and in modified smoker history. So if you
Yeah.
see that the RMS error and the MAE, means square error and correlation, if you
Yeah.
see that
Mm.
for every aspect our Bayesian model performing very well. That is, if you see the correlation part, that is point 0.8. It's a huge.
So
So
correlation, if it's close to one, is the best, right? And below
yes,
and one,
yes,
right?
yeah,
Okay.
yeah.
Yeah.
So it's point 0.1. So there is a difference, point 0.1. It's a huge.
Yeah. Yeah.
it's yeah. So yeah, so we got this result. So we are happy that our model is working very well on those data sets. So these are the results we got. Yeah.
Great.
Next.
So
So
conclusion, yeah.
yeah. So in the conclusion part, yeah. So what I we got on this, that the posterior distribution of unknown model parameters of interest are obtained by drawing sampling using the multidimensional stochastic process using
Mm-hmm.
MC method. Okay, and we did two chains. We by realizing total 6,000 sampling. Okay,
Hmm.
and after that it's converges. So we used all those two chains in using MC sampling in two wells, and both two wells performed very well, and we got very good result for those.
Hmm.
And second thing is Bayesian inference helps to quantify the prediction of uncertainty. What I just
So
said.
one thing, Akash, just to
Yeah.
clarify, so once you have this model which has performed well,
Hmm.
you take this model to some unknown data also, and
Yes. Yes. Yeah.
or
Yeah.
yeah, okay, and you
Yeah.
check
You
that
can use.
how much,
Yeah.
yeah, okay,
Yes.
got it, yeah.
You
Hmm.
can use, and the parameter also you can take if you have want to calculate different parameter, like if you want to calculate any other things, you can also use that this model also.
Oh,
But
okay, I see.
the
Mm-hmm.
coefficient would be different because the posterior would be different if your data sets distribution would be different. So your data, the coefficient value that we take, the mean value of this posterior distribution would be different. But I think, but the result would be really good rather than the
Okay,
deterministic model.
I see. Mm-hmm.
And also this model also give you the uncertainty, that what are the confidence 50% and 95% confidence interval you will get if you use this theorem, if you use this method in your
Mm.
data sets. And also yeah, and this Bayesian setting performs really well also. And in the lab also we try to compare with our laboratory measured ToC value, and
Mm-hmm.
we seen that it gives a very good result. And
Great.
yeah, and also the proposed model is proven to be better suited for predicting high ToC content with higher accuracy in the our
Great.
in the lower Silurian shale deposit, mainly in the during the kind of shear conditions, and irrespective of the shift in the division environment within the same formation. So, so mainly the formation was the Silurian shale. So, if children's shale is a TOC content is high, we'll get much more very good result on that part.
Okay,
So
well,
that's some whole conclusion we got on this.
great.
So if you compare with the machine learning, I think yeah, machine learning there is one limit, that is data. You need lots of data sets. But in geostatistics, if you have the data set that shows the original distribution, the data should maybe there is a less data set, but the data set, if you what you have, if it shows the distribution, you can predict. You can predict the parameter you
How
want to.
about some synthetic data set? If you put a
Hmm.
little bit of synthetic data set in this,
Okay.
yeah, then I mean
Yeah,
there are
because
now better models like such as transformers, which can also
yes,
you can
because
use hmm
but it follows the it should follow the distribution.
the distribution.
If
Okay, I
yeah,
see.
it's
Mm-hmm.
totally what the result we will get. It's totally depending on the distribution. So if
Mm.
distribution, if it's correct, if your synthetic model also give the value that also aligned with the distribution, you will get much more good result also.
I see.
So that is the main thing.
So what is next for after this research? Like, what would be the next step of the research, or where is this applicable right now, the studies and
Yeah. So currently, for after joining Shell, I don't have much scope to work on this.
okay,
But
yeah,
but yeah, really interested to make it next level. I'm not sure in future if I get any chance. But I think it would be really helpful in industry purpose also. And and I think it will help in future also. And yeah, that's all. No
So
problem.
this data, was it provided by industry to you, or
I'm not sure. Actually, my guide was Shikshanka. So
oh, okay,
he collaborated with those guys, and they tried
okay.
to we convince them that we can do something with those data sets. We can
Mm-hmm.
predict something. So yeah, so whole
Okay.
those.
So, in general, like in a higher level, you mentioned this can help your in oil and gas industry. So, where exactly? Maybe we can maybe discuss, and if oil and gas people are listening to the
Yeah,
podcast,
yeah.
they might be interested. Yeah.
Yes, so it's a TOC is a total organic carbon. So if there is a TOC is present, so
Yeah.
there's a high probability that we might get some oil attributes or some gas attribute might be there. So in those prospect, so TOC is very useful also.
Mm,
So if
okay.
you know that is
Yeah.
very high TOC value is there, so we can do much more dive into those area. We should focus much more on those area on the depth. If that depth have
Okay.
very high TOC value.
Ah, I see. No, it's a very interesting study. Vishan, do you have questions for Akash?
It's all good. See, you've done a lot of things, and I think also you said that now you are doing some manual work.
Yeah,
But
actually,
you're
and
go ahead.
actually,
What's
yeah.
your work
So
now? Maybe you can tell us a bit about that.
yeah, so my work is mainly I working on the seismic data management. So in Shell we are mainly we take all those data sets from all over the world, what
Hmm.
the assets we have. So we
Hmm.
got all those data sets, but we get in raw format sometimes. So we need to sometimes do some processing on those data sets. We need to prepare those data sets to so that someone can interpret.
Hmm.
So we are managing all those data sets. We are their formatting and there some processing part or some if there is some error or something. So we fix those in the navigation part. So navigation also a big problem in seismic, you know. So if so in the geodetic, we always do sure about the geodetic integrity. So this one thing, and sometimes we don't have the navigations also. So we try to manage all those things and prepare those data sets so that someone can do some interpretation on that.
So how big are these data sets? Like terabytes and all?
Yeah, yeah.
How,
It's
oh my
yeah.
God. How
I
much do you process in a
still
day?
it's a huge. Actually, the big problem is this in the seismic data set. It's a huge problem,
Yeah.
and you know that number of companies are now creating their one cloud that is HPU. So one common partner will be there. So
Hmm.
that any geophysicist or someone can get the data sets from there. So
Okay.
all the industries are working on those and in the HDU part that is seismic data universe. So
Mm-hmm.
number of company like Exxon, Schlumberger, all the company are give their interest to make this cloud. So we are, I think, for us it would be in future will are the key person for those also, and lot of things are happening on those things in the coming days. So this is the main thing, man. The seismic data sets, the main thing is the size. You can't extract this data sets anywhere, any minute, in a second. You need the storage, okay, and for storage you need to give money for that, and it's a huge cost. So
Yeah.
that is the thing. So we are trying to improve the process that how easily we can get the data set in a day if we want. So we are trying. It's a long process. So yeah, that is the main thing. And yeah,
Okay. Sounds good. Well, thank you, Akash, for sharing your research, which is really interesting, and also with the work that you do at Shell. and we hope all the best for you. And I hope this research gets in some next stage. I
Yeah,
definitely
sure,
think.
sure, sure.
Yeah, and
If
we'll
in
again
future.
invite you for the
Yeah,
podcast.
yeah,
Okay.
sure, sure.
Yeah. Thank you.
Thank you.
Thank you, Vishal. Thank you, Tanisha.